Imagine stepping out into the vacuum of space, tethered to a floating laboratory 400 kilometers above Earth, while the brightest planet in our evening sky gleams right beside you. Today, while astronauts gear up for a major spacewalk, the sun is offering us a remarkably calm window. But why do we so often confuse a sudden burst of light from our star with a billion-ton cloud of plasma? You're listening to the Daily Space Podcast by Flarient, your daily conversation about space weather, solar activity, and cosmic events. I'm Ollie, and today is Monday, August 24th. Let's get into what the sun is doing today. Looking at our live numbers coming in right now from the Space Weather Prediction Center, things are extraordinarily peaceful across the heliosphere. The Planetary KP Index, which measures global geomagnetic activity on a scale from 0 to 9, is sitting at a quiet 0 to 1 level for most of the morning. Over the last 24 hours, the absolute peak KP value recorded was just 1.67. Now, what does a KP of 1.67 actually mean for you and me? In plain English, it means Earth's magnetic field is virtually undisturbed. When the KP index stays below 3, the magnetosphere is in a relaxed state. There are no geomagnetic storms underway, power grids are operating without any induced currents, and satellite operators can breathe a sigh of relief. Checking our disturbed storm time or DST index, we are hovering around -10 nanoteslas, with quiet baseline estimates near -29. Remember, the DST index tracks the ring current around Earth. Deep negative numbers, like -100 or -200, signal major geomagnetic storms. A value of -10 is practically baseline noise, confirming that Earth's magnetic shield is smooth and steady. Our solar wind speeds are also very modest today, averaging roughly 388 km per second with low plasma density around 2.2 particles per cubic centimeter. The interplanetary magnetic field has a slight southward BZ component of -1.5 nanoteslas, which is far too weak to open up the magnetic field lines for significant energy transfer. What does this mean for aurora chasers tonight? Well, aurora activity is currently suppressed and confined to high polar latitudes. Unless you are located deep inside the Arctic Circle, you probably won't see green curtains dancing across the horizon tonight, but these quiet conditions are actually fantastic news for space operations. Speaking of solar dynamics, let's dive into some of our latest articles published on Flarient.com, starting with a classic point of confusion: solar flares versus coronal mass ejections. How often do you hear headlines mixing up flares and CMEs as if they are the exact same thing? It happens constantly in mainstream news, right? But physically, they are completely different phenomena with entirely distinct arrival times and impacts on Earth. A solar flare is fundamentally a flash of light, an intense blast of electromagnetic radiation across all wavelengths, from X-rays to ultraviolet light. Because it is light, a flare travels at 300,000 km per second, taking just over 8 minutes to travel from the Sun to Earth. When a solar flare strikes, it instantly ionizes the upper layers of our atmosphere on the sunlit side of the planet, causing high-frequency radio blackouts almost immediately. A coronal mass ejection, on the other hand, is not light. It is a gigantic structure of solar plasma, billions of tons of charged particles threaded with magnetic field lines. CMEs move much slower than light, traveling anywhere from 400 to a few thousand kilometers per second. That means a CME takes anywhere from 15 hours to 3 full days to reach us. When a CME hits Earth's magnetosphere, that is what triggers full-scale geomagnetic storms, brilliant auroras, and electrical grid currents. So to keep it simple, flares are the flash, and CMEs are the cannonball. A flare hits in minutes, while a CME arrives days later. This brings us to another article exploring how solar flares are proven, highly measured scientific events rather than theoretical concepts. As Solar Cycle 25 continues its active phase, our satellites like the Solar Dynamics Observatory capture these intense events in real time through magnetic reconnection. When magnetic field lines above sunspots become twisted and stressed, they snap and reconnect, releasing energy equivalent to millions of hydrogen bombs exploding at once. We classify these flares on a logarithmic scale, A, B, C, M, and X. Each letter step represents a tenfold increase in X-ray flux. An M-class flare is 10 times stronger than a C-class, and an X-class flare is 10 times stronger than an M-class. Understanding these scales helps satellite operators protect sensitive electronics. Now, let's turn our attention from the Sun to deep space and address a fascinating astronomical question: could an asteroid ever grow larger than Earth? Sci-fi movies love to depict world-sized rocks hurtling through space, but fundamental physics tells us why that simply cannot happen in our solar system. Asteroids are leftover building blocks from the early accretion disk. By definition, if a body in space grows large enough, its own gravity pulls it into a sphere, a state called hydrostatic equilibrium. Once an object achieves hydrostatic equilibrium, clears its orbital neighborhood, and forms a core, mantle, and crust, it becomes a planet or dwarf planet, not an asteroid. The largest object in the main asteroid belt is Ceres, which is roughly 940 kilometers across. Earth, by comparison, has a diameter of almost 12,742 kilometers. Even the infamous Chicxulub asteroid that caused the extinction of the non-avian dinosaurs was about 10 to 15 kilometers wide, destructive on a planetary surface level, but a tiny speck compared to Earth's mass. Our fourth article tackles the elegant physics of satellite orbits. How do thousands of spacecraft remain above our heads without falling back down? As Sir Isaac Newton illustrated with his famous cannonball thought experiment, satellites are essentially in a perpetual state of freefall toward Earth. They travel sideways so quickly, around 7.6 kilometers per second for the International Space Station, that as gravity pulls them down, Earth curves away beneath them at the exact same rate. However, low Earth orbit is not a complete vacuum. High atmospheric density caused by solar heating can create drag, slowing satellites down and requiring periodic orbit boosts. That balance between gravitational pull, velocity, and solar-induced drag is what orbital engineers monitor every single day. Moving into our space events, we have a brilliant week lined up for observers on Earth and astronauts in orbit. First, planetary observers are in for a treat tonight as Venus reaches its greatest elongation east, standing high above the western horizon right after sunset. This position puts Venus at its maximum angular separation from the Sun as seen from Earth, offering the clearest and brightest evening viewing conditions of the year. If you step outside just as twilight fades, Venus will shine like a brilliant diamond in the western sky. You don't even need a telescope, it's visible to the naked eye. Meanwhile, ground tracking networks are keeping an eye on near-Earth asteroid 2022 UP6, which makes a routine close approach today. Rest assured, 2022 UP6 is passing at a completely safe distance with zero chance of impact, but these close flybys provide astronomers with valuable radar data to refine orbital models. Up aboard the International Space Station, preparations are underway for US Spacewalk 98, scheduled for August 25. NASA astronaut Anil Menon and ESA astronaut Sophie Adenot are getting ready to step outside the orbital complex for critical maintenance work. Their primary task during this spacewalk is replacing a degraded space-to-ground antenna system, which is vital for high-rate data relay and crew communications. Now, let's tackle a quick fact-check segment based on common space claims making the rounds online. Claim number 1: a single solar flare can blow Earth's entire atmosphere into space. Verdict: false. While solar flares emit intense X-rays and extreme ultraviolet radiation, Earth's strong global magnetic field and dense atmosphere absorb this energy harmlessly high in the thermosphere and ionosphere. Flares cause high-frequency radio blackouts and satellite drag, but they lack the physical mass or mechanism to strip away our atmosphere. Claim number 2: satellites float in space because there is zero gravity at their altitude. Verdict: false. At the altitude of the space station, around 400 kilometers up, Earth's gravity is still roughly 90% as strong as it is on the surface. Astronauts and satellites experience weightlessness not because there is no gravity, but because they are in continuous freefall around Earth at high orbital velocity. Now for our daily brief, bringing together today's top operational highlights. Today's main highlight centers on the ideal conditions surrounding the upcoming ISS Spacewalk by Anil Menon and Sophie Adenot. With the KP index sitting at a steady 0.33 and solar wind speeds remaining quiet around 388 km per second, space weather risks for the crew are virtually non-existent. During intense geomagnetic storms or energetic particle events, extravehicular activities can be risky due to increased radiation doses and potential satellite communication disruptions. Fortunately, NOAA's Space Weather Prediction Center reports zero threat of significant flares or coronal mass ejections over the next 24 to 72 hours. This tranquil space environment allows mission control and the astronauts to focus entirely on replacing the space-to-ground antenna without worrying about unexpected solar disturbances. Combined with the spectacular evening appearance of Venus and routine tracking of asteroid 2022 UP6, today is a perfect demonstration of science, operations, and observational astronomy working in tandem. That wraps up our main coverage for today, but before you go, here are a few quick reminders. Head over to flarient.com for live space weather data, real-time KP index updates, aurora forecasts, and interactive solar dashboards. It is the official website of Flarient and the best place to see exactly what the sun is doing right now. Make sure to subscribe to the podcast on your favorite platform so you never miss a daily update. You can also visit flarient.com/podcast for all previous episodes, full transcriptions, and show notes. Don't forget to follow Flarient on social media for real-time space weather alerts, and join our vibrant community of aurora chasers and space enthusiasts. Finally, download the Flarient app on iOS and Android to get instant push notifications whenever geomagnetic storms hit. Thanks for tuning in. I'm Ollie, keep looking up, and I'll catch you again tomorrow on the Daily Space Podcast by Flarient.